Buenos días a todas y todos. Bienvenidos al evento Seminario en Biomateriales y Sustentabilidad, que se celebra en el marco del 50 aniversario de nuestro Departamento de Madera, Celulosa y Papel. Es un honor para mí estar aquí con ustedes en este momento tan especial. Hoy aprovecharemos la oportunidad de reunirnos con exalumnos de la Maestría en Ciencia de Productos Forestales, que fueron becarios del DAD, quienes son expertos en diversas áreas de los biomateriales sustentables. Además, contaremos con la presencia de académicos, emprendedores y empresarios relacionados con nuestro campo. Agradecemos sinceramente la presencia y el apoyo de todos los participantes en este evento. Este evento no sería posible sin la dedicación de los organizadores y colaboradores, a quienes también agradecemos profundamente. Para comenzar, tengo el placer de presentar al presidium de nuestro evento. Por favor, reciban con un fuerte aplauso a nuestros distinguidos miembros, el doctor José Antonio Silva Guzmán, jefe del Departamento de Madera, Celulosa y Papel. Al doctor Ricardo Manríquez González, coordinador del doctorado en Ciencia de Biomateriales Sustentables y organizador de este evento. Al doctor Iván Benson, investigador de la Universidad Federal de Paraná, Brasil. Y a la maestra en ciencias Marianely Esquivel Alfaro, investigadora de polímeros naturales de la Universidad Nacional de Costa Rica. Ahora invito al doctor Antonio Silva a dirigirse a nosotros con unas palabras de bienvenida.
Muy buenos días a todos. Es para mí un privilegio estar aquí con ustedes esta mañana para darles la más cordial de las bienvenidas a este evento de biomateriales y sustentabilidad, deseando que tengan mucho éxito todos los participantes. Primeramente quiero agradecer al ITRANS, a la doctora Ruth Padilla Muñoz y también a la licenciada Edith Padilla por las facilidades para poder realizar este evento aquí en sus bonitas instalaciones. Este es un evento más que estamos realizando dentro de este aniversario de los 50 años de la fundación del Departamento de Madera, Celulosa y Papel. Y de aquí a fin de año todavía vamos a estar realizando algunos eventos académicos que consideramos importantes. En su momento se los vamos a dar a conocer también. Como ustedes saben, nuestra institución fue fundada por el ingeniero Carl Austin Grellman, que tenía una visión muy, importante de las cosas. Él vino en los años 50 aquí a México y formó nuestro departamento por ahí en el año de 1973. Y siempre nació con una fuerte visión y vinculación internacional y también de la realización de investigación aplicada para que resolviera las necesidades y problemas que tenía la industria, en ese caso de celulosa y papel principalmente, y también la parte de madera. No es nuevo, ustedes conocen muy bien que las universidades son los motores que deben promover el desarrollo económico mediante la innovación y el desarrollo sustentable de los países, generando la transferencia de conocimiento mediante una estrategia metodológica sistemática. En todos los países así funciona, las universidades generan los conocimientos, los transfieren y los que ya se encargan de hacer realidad, pues y hacer el dinero son los industriales. O en este caso, si se resuelven necesidades, pues los gobiernos o también la misma sociedad. La función que tenemos nosotros como Universidad de Guadalajara, como CUSEI y también como Departamento de Madera, pues más que educar es transformar las vidas de las personas que vienen a estudiar con nosotros. Y mediante esta transformación que hacemos, ellos adquieren los conocimientos, las habilidades y las destrezas, y también esto les va a permitir ser exitosos en su campo de desarrollo también, y buscamos que en su vida personal, porque tenemos que poner en el centro de toda esta educación y esta formación a la persona, ¿verdad? Porque finalmente es muy importante. No es nuevo también, los biomateriales sustentables siempre ha sido un tema muy importante, un tema de vanguardia a nivel mundial. más de 5,000 productos que los que usamos todos los días provienen de madera o de materiales base madera. A lo mejor me están juzgando, dicen, pues conocemos tablas, conocemos muebles, pero hay más,
siempre ha sido un tema muy importante, un
incluyendo
tema
también.
de vanguardia a nivel mundial. Más de
Entonces ahí tenemos cuestiones nano muy interesantes para aspectos biomédicos, para cuestiones electrónicas. Es un mundo muy valioso y obviamente para esto se requiere la generación de conocimiento. Estos eventos internacionales son muy valiosos para lo que tiene que ver con el desarrollo institucional del Departamento de Madera, porque pues, tiene sólida vinculación con muchos países. En este caso, durante toda esta trayectoria y a través de la maestría y con el apoyo del Departamento de Intercambio Académico Alemán, se han formado personas de Nicaragua, de Costa Rica, de Venezuela, de Colombia, de Perú, de Argentina, Chile, también de Brasil, en este contexto que nosotros tenemos. Ellos vinieron becados por mucho tiempo y luego hicieron su maestría, se graduaron con nosotros y después continuaron con doctorados, pero los conocimientos que adquirieron aquí en su formación fueron muy importantes para ahora después ellos ser exitosos profesionistas en sus países donde ellos trabajan. Entonces, eso es muy, muy importante. De alguna manera han estado también ligados con nosotros y seguimos realizando algunos proyectos. Eh, Tengo entendido también que parte de los objetivos de este evento es que generen, si bien tenemos una asociación ya de egresados de esta maestría, pues una red que realmente colabore, que desarrolle investigación de alto impacto. Alto impacto no es que publiquen en el Journal de Impacto 20, sino que realmente resolvamos los problemas que la sociedad y las industrias sí tienen. Y hay un andamiaje, hay una metodología sistemática ya muy conocida, que obviamente nosotros no la hacemos, no la utilizamos, damos un servicio y pues ahí muere. Pero bueno, de hecho ahorita el CUSEI está en un proceso de capacitación formando una masa crítica con profesores del MIT para buscar que esa innovación y esa transferencia de conocimiento pues realmente impacte. Y les digo, no hay que andar descubriendo hilo negro, ya el caminito se conoce, pues nada más hay que implementarlo. Quiero finalizar nada más con una cita de Daniel Seidman, que es presidente del Instituto Helmholtz Research for Grand Challenge, que es una institución alemana que realiza investigación de vanguardia para encontrar soluciones a demandas importantes y urgentes, no nada más de la industria y de la sociedad, sino también de la misma ciencia de las universidades. Él establece que la próxima revolución científica será impulsada por científicos quienes tengan una visión multidisciplinaria de la ciencia, la oportunidad de asumir y correr riesgos y que cuenten con la infraestructura para trabajar y plena libertad de pensamiento. Algo que también nosotros conocemos muy bien, siempre este trabajo interdisciplinario, y no me refiero nada más a los expertos de la parte de los biomateriales y la sustentabilidad, sino ahí entra el diseñador, entra el físico, entra el matemático, entra pues de la cuestión de la administración de las ciencias económicas, o sea, tenemos que hacer esta interdisciplinaridad de las ciencias para poder nosotros atender de una manera integral esta problemática. La sustentabilidad, pues ustedes saben, ahorita es la palabra de moda y las instituciones que no estemos haciendo investigación que sea sustentable, pues estamos fuera, ¿verdad? Entonces, la invitación es esta. Finalmente quiero agradecer mucho a la doctora Ruth Padilla Muñoz, su hospitalidad aquí con nosotros y pues siempre ha sido una gran amiga, compañera y ha cuidado el desarrollo del departamento desde su fundación. También al doctor César Monzón, que es nuestro director de división, y les agradezco mucho su presencia en este acto esta mañana. Bienvenidos todos y disfruten su evento y el mejor de los éxitos. Gracias.
A continuación, el doctor Ricardo Manríquez nos ofrecerá unas palabras.
Hola, tal? Buenos días, bienvenidos. Doctora Ruth Padilla, muchas gracias por prestarnos estas instalaciones que son de verdad para nosotros un gran apoyo para que este evento sea todo un éxito. Gracias, doctor. Monzón por apoyarnos todo el tiempo en la parte de la división de ingenierías. Bienvenidos todos a este seminario de biomateriales y la sustentabilidad. Yo creo que el doctor Silva pues ya resumió muchas de las cosas que iba a comentar, pero solamente me voy a enfocar en 2 puntos. Uno, en la cuestión de la visión que tenemos de los biomateriales y la sustentabilidad, que es el principal objetivo de este evento. Desde hace 2 años iniciamos con un programa de doctorado que es el de Ciencia de Biomateriales Sustentables. Y la visión no es que sea simplemente adaptarnos a lo que es lo que las tendencias nos indican, sino en realidad es tratar de volver la mirada hacia a lo que en realidad hemos perdido, ¿no? Entonces, tratar de regresarnos a ese punto inicial que es ver la naturaleza y entonces ver cómo también retribuye a la naturaleza lo que nos ha dado. Y entonces esta es la visión del doctorado. Por lo tanto, lo que nos impulsa a generar este tipo de eventos es lo que en realidad hemos perdido, ¿no? Nuevamente el interés de todos los que se quieran sumar a esta propuesta. Empezamos hace 2 años, ya tenemos ahorita nuestro primer evento, esperemos que no sea el único. Contamos también con mucho el apoyo, no solamente de las autoridades, sino también de grupos de investigadores que están todo el tiempo tratando de generar buena interacción y combinación, ya sea para generar ciencia básica o ciencia aplicada. No me queda más que pues agradecerles que hayan tomado el tiempo y las ganas y abrir la oportunidad a que se pueda haber discusión. Eso es un foro también de discusión donde se van a ver diferentes temáticas. Y la idea es que no solamente se vean pláticas, sino también haya momentos de hacer discusión científica o transferencia de conocimiento, que también los estudiantes tengan la confianza de venir y platicar con los ponentes y poder verse reflejados en cómo pueden plantear su futuro. Agradezco mucho a todos por su asistencia y de verdad espero que esto sea un éxito. Muchas gracias.
Seguidamente escucharemos al doctor Iván Benson.
Olá, bom dia. Primeiramente, me gostaria de agradecer ao professor Ricardo, professor Silva, doutor, e a comissão de organização por el evento, por la invitação, e dizer que a grande satisfação, a grande alegria de volver a México, volver ao DG, ao departamento onde hice minha maestria, com o fundamental apoio do DAD, né? E já se passaram 20 anos, 21 anos, e uma grande satisfação volver e dizer-lhes que todo o tempo que é passado aqui foi definidor de minha trajetória, foi lo llevé adentro e tudo que foi aprendido, foi construído aqui, me levou a ingressar na universidade, en la carrera de investigador, de docente. Nuestros países, me imagino que são algo semelhantes, temos grandes desafios, em um mundo que vai cambiando muito rápido, e a sociedade, todo o mundo nos espera de nós respostas, definições, certezas. Estamos aqui para isso. Então, não vou falar demasiado, mas me gostaria muitíssimo que tuviéramos a oportunidade de platicar, de estabelecer conexões, porque isso é fundamental neste mundo. Se, como disse o Dr. Silva, se buscamos a ser diferença, a ser coisas de impacto, isso só se alcança com muitas conexões, com trabalhos com muita gente, muitos expertos, e isso é o que buscamos acá. Então, finalizo agradecendo, manifestando que seja um excelente evento, que possamos discutir muitas coisas, temas acadêmicos, temas de respeito à sustentabilidade, sobre seus diversos aspectos que isso apresenta, ok? Muitas graças, desejo que seja um excelente evento e que possamos passar esses 2 dias em contato e platicando a respeito. Muitas graças.
Finalmente, invito ahora a la maestra Marianelli Esquivel para que nos dirija unas palabras.
Buenos días un gusto estar aquí. Para mí siempre es un gusto volver a Guadalajara. Yo creo que voy en la misma línea mis palabras de agradecer a la organización por la invitación, agradecer siempre el apoyo del DAD que nos permitió en su momento ser estudiantes becados y ahorita volver a un evento como este. Y pues yo tengo que decir que a mí me marcó mi carrera profesional y mi carrera personal. Porque mi esposo es tapatío y lo conocí durante la maestría y siempre es un gusto volver a Guadalajara. Yo trato siempre de mantener el contacto. Hemos tenido estudiantes nuestros que han venido a hacer pasantía, hemos tenido profesores que hemos recibido y creo que parte del objetivo de la actividad estos 2 días es retomar esos contactos, seguir colaborando porque necesitamos trabajar conjuntamente porque somos de diferentes países, pero tenemos problemas muy similares con diferentes realidades, pero hoy en la mañana que conversamos tenemos problemas muy similares en términos de contaminación, residuos, sostenibilidad, que tenemos muchos retos. Costa Rica, por ejemplo, es un país que tiene fama de ser muy verde, pero hay unas cosas que no son tan verdes. Entonces tenemos muchos retos por lograr, ¿verdad? Y que puedan impactar también a las comunidades. En nuestro país, por ejemplo, tenemos comunidades donde se da, por ejemplo, producción de piña, que son de las comunidades con más rezago en términos de incluso derechos humanos. Entonces tenemos muchos retos y queremos impactar en esas comunidades a través de la investigación multidisciplinaria. Bueno, agradecer el espacio y espero que el evento sea un gran éxito. Gracias.
Muchas gracias a todos nuestros distinguidos miembros del Presidium por sus palabras. Antes de continuar, quiero tomar un momento para agradecer la presencia de algunas personas muy especiales en nuestro público hoy, a quienes invito a ponerse de pie. En primer lugar, la doctora Ruth Padilla Muñoz, directora del ITRANS, quien amablemente nos facilitó las instalaciones para este evento. Al doctor César Octavio Monzón, jefe de la División de Ingenierías. La maestra Montserrat Molina Díaz, jefa de Unidad para el Fomento a la Internacionalización. Al maestro Ricardo Vizcaíno Meléndez, responsable de internacionalización del currículo. Y no sé si se encuentre con nosotros la maestra Valeria Viridiana Padilla Navarro. Muchas gracias. Bueno, pues su presencia enriquece nuestro evento. Muchas gracias por acompañarnos. Ahora, para dar inicio formalmente a nuestro evento, tengo el honor de invitar al doctor José Antonio Silva a que proceda con la apertura oficial.
Hoy 13 de junio, siendo las 9:20, declaro formalmente inaugurados los trabajos de este seminario de biomateriales y sustentabilidad y deseando el mejor de los éxitos. También aprovecho para agradecer la presencia del doctor José Rutiaga de la Facultad de Ingeniería de Tecnología de la Madera de la Universidad de Michoacana que nos acompaña y también el ex becario del DAD. Y pues felicidades y mucho éxito y gracias.
Bueno, muchas gracias. Tomamos asiento para iniciar nuestro evento de apertura con nuestra primera conferencista. Es el doctor Sven Henning. No sé si ya nos escucha el doctor Sven.
Hello.
Hi, Sven.
Hello, can you hear me?
Alles in Ordnung.
Dankeschön.
Ah, bitte. Bueno, voy a hablar un poquito sobre el doctor Sven Henning, hablando un poquito de la semblanza de su trayectoria. El doctor Sven Henning estudió física en el Martin Luther University en Halle, Wittenberg. I don't know, I have to do it in English for you. It's better for you?
Oh, it's fine if you do it.
Okay.
However.
Okay, let's change. Sven Henning studied physics in the Martin Luther University Halle, Wittenberg. and he received a diploma in 1994 for the thesis entitled Electron Microscopy Studies in Biodegradation of Polymers. And he received his PhD in 2006 for the thesis of the title Morphology and Micromechanics of the Bond and the Partially Resorbed Bond Cements. Since 2010, Sven is scientist in the Fraunhofer EWM and Fraunhofer EMWS Halle in Germany. And from 2013 to 2015, he was the group leader of the evaluation of the materials of the medical technology on the Fraunhofer in Halle. Since this year, he is team leader of the polymer analytics in the Fraunhofer Institute, and he is a lecturer of the polymers material science since 2012 in the Technical University in Immenau in Germany. Since 2019, he is the vice president of the Polycharts on the award committee. Actually, is the time when I met this guy, and I really enjoyed to discuss some topics with him. The research topic of the electron microscopy of the polymers and biomaterials with the focus on the structure, processing, properties, correlation, and the analysis of the mechanical process of the formation of the fracture. The scientific work is dedicated to the development of the fuel saving and the resistant tire rubbers, bio-based polymers, and the tolerant properties, biodegradable polymers, and the polymers of the biomedical application. I can say too much things to him. Actually, he's really good teacher and he's really good friend. And Sven, show time.
Oh, thank you very much. I just want to be sure. Can you hear me loud and clear?
Yes.
Excellent. And you can see my slides probably?
Yes.
Excellent. So just tell me if there is any problem. You know, I'm far away. I'm in Germany at the moment. First of all, thank you very much for the opportunity to speak. There was the invitation to come to Guadalajara, but we just finished our own conference yesterday, conference on biopolymers, very much connected to our region. So I was not able to travel, unfortunately, but I'm quite sure that I will do that someday. I have very, very strong connections to Mexico. I've been to Mexico several times, so it is time to come back to you. Just let me start with my talk. I'm not going to tell you about what Fraunhofer Institute is. We are an institution with about 60 institutes, starting from defense, industry, going to biomedical materials, informatics, and so on, with a lot of people contributing to our success. Today, I would like to take the chance to talk about my region, about the region where I grew up and the problems that we had connected to the chemical industry and the different transformations we have seen in our life. So the title of the talk is Bio-based polybutylene succinate compounds for injection molding application. The research is funded by the German Ministry of Education and Research, and you can see also the many people that are contributing to the beautiful project. So let's get started. I would like to give a short introduction on the transformation that we see in our region. And that's the situation we are facing at the moment. So you can see this is Germany. We are in the middle of Europe. And in the middle of Germany, there's a region which was East Germany, which was German Democratic Republic earlier. So we have seen transformations 30, 35 years ago, and we are now just facing another transformation that is due to environmental aspects of polymers and chemistry, and due to the shortening of energy, the shortening of gas, especially, that we do not get anymore from Russia due to the war in Ukraine. So that all has impact on the situation. And in middle of Germany, former East Germany, there's a region that is very strong in chemistry from all the history. So what we do is we face challenges that are mainly due to a shortage in gas delivery. So the feedstock, the energy that we need for our chemical industry, is getting more and more expensive. So that leads to economic crisis. Of course, we also have to deal with the carbon footprint that is connected to chemistry and polymers and the climate change. You all know about the problems. We are discussing that for years, and it's time now to do a change. And of course, we are also talking about the ecological impact of the polymer waste. So there is now, fortunately, an approach. There's a solution coming up. And first of all, for our science is that the solutions are triggered by political decisions. So there is a strong national economic support. That means there's a lot of money coming in at the moment. And on the other hand, we have a technology push. So we have now the technologies, we have now biochemistry, we have the materials to go into a bio-based polymer situation. So that is it, what I'm talking about. We have now a conversion from coal, from oil and gas to bio-based feedstocks. That is the situation. That is the region where I grew up. So since 1916, there is a strong chemistry developing based on brown coal. The brown coal was mined in open cast mining in Germany. You can see the devastation of the landscapes that we have experienced due to the brown coal mining. And the place where I come from was the place where the first synthetic rubber was produced. The polybutadiene rubber since 1936, last century, was produced just next door to the place where I sit at the moment. In the 60s, we had a transformation to petrochemistry, and now we are going to open up a new chapter. So that is the vision we have. Yeah, there is a big money coming from the transformation fund that enables us to go from coal to green resources. And there's just one example. I've just had a message 2 days before that there will be a Center for the Transformation of Chemistry at the campus of our university, the University of Merseburg, University of Applied Sciences, with a lot of money. And this is a banner that is hung up just a couple of days before, which is telling you chemistry is coming home. We have been a very strong region in chemical industry, chemical education, and now we have the chance to start again with new also education, with new students, new funding for new institutes. That is great news for us, and I'm very happy. So what is the vision? What we want to do is to go to natural feedstocks, to biological feedstocks that are at hand, for instance, starch, sugars, but also plant waste, to go all these waste that you can see here to come finally to products like polybutylene terephthalate, PBAT, PBS, the material I'm going to talk about today, but also what we are just doing at the moment already is to produce, for instance, polyamides based on finally biological feedstocks. And you can see here the prognosis that we have to the year of 2028, that we have a steep increase of the production capacities for bio-based polymers. You will probably not be able to read all the details over here, but that is exactly what you expect. So what we can say is that now we have seen several waves of bio-based polymers. We had the starch-based polymers in the 90s coming up. We had the PHB, or the polyhydroxyalkanoids, coming up, and so on and so on. But today we are talking about not having the next wave, but having a tsunami that is coming up with the bio-based polymers. And that is where we want to have our share. Let me give you some details on the material that we have chosen. We are going to polybutylene succinate PBS material for the applications we have in mind. So the idea is to go to green synthesis, and we are looking for applications. And of course, the standard application, if you think about polymers, would be packaging, to have hygienic items that you can use like toothbrush, like packaging in a medical field. But you will see later that we also focus on demanding applications. We want to go to automotive industry, for instance. So the idea is that we come from a regenerative feedstock, and we have, for instance, plant-based waste. We are going to collect green cut. We are going to collect plant-based waste, do a chemical extractions to get the starch, the sugars, and so on. And with fermentation, we can produce succinic acid and butanediol, which are the monomers that we use for the PBS polymer. And to tell you the truth, the succinic acid works quite nicely. The butanediol still is a problem. We don't have the capacities at the moment to get our monomers by ourselves. This is just a scientific project we are doing at the moment. We have gained a couple of kilograms of the PBS from our own resources, from our own pilot plant, but at the moment we are forced to buy the monomers and to buy the feedstock in China. So after that, we do the polycondensation, we get the polybutylene succinate that can then go to biodegradation, or even better, goes to recycling. The idea is to produce a plastic material, a polymer with excellent properties that can be recycled, because the biopolymers still are much more expensive than comparable mass production polymers like polyethylene, polypropylene. So what we have to do is we have to feed our beautiful materials, our expensive materials, back to recycling. And that is one of the strategies that we follow. In our region, we have formed a consortium of 18 enterprises, small, medium enterprises and research centers that are working in the field of biotechnology, working in the field of polymer synthesis, working in the field of compounding, processing, and recycling. And that all together gives us the chance to have the vision to go from fossil-based feedstock to the green one. You see, that is the politics we do. You have the bad side, you have the black and the dirty one, and we go to the beautiful green thing. I know that it's quite quite strong and quite political, but that is finally the aim where we want to go in our region. We have a compact production system in mind, going from fermentation all the way to polymerization, compounding. And if you like, there would be also a nice movie, a nice video that will show you all the different steps, and you can see all the different things that we have here, starting from the production of the feedstock, of the generation of energy, fermentation, polymerization, up to the compounding and production of these green materials. That is exactly what we are talking about at the moment with the government of our state to get the funding for this facility to be set up at the industrial site of Schkopau in our region. So that is something that will come up probably during the next years. Good. Let me summarize the polybutylene succinate story. The target is to have sustainable products made of green polymers, bio-based, recyclable, and if there is no other chance, also to be able to biodegrade. You can see again the cycle over here. And there's one thing that I have to mention. If we talk about biodegradation of polybutylene succinate, we have to keep in mind that it does not degrade in the environment. It does not degrade in marine environment. We have to have defined composting conditions so that we have a biodegradation. So that is a limitation. The first aim is to go to recycling. What we do is substitution of commodity plastics like polypropylene, polyethylene, mainly based on plant waste. We are not going to go into the food cycle. We are not going into the things that you need for nutrition. The aim is to develop products for demanding applications as there are automotive, car interior, exterior parts. We are designed for recycling, and at the end of life, we can go to composting facilities if we have the right conditions. Okay, here you can see an example that is just the photographs from 2 days before on our conference. We can do these high-value cups from material of PBS that's called biosilane, similar properties as porcelain. You can see all these items over here, soft items, films, stiff items. Here is a gardening set produced of our biomaterial, just to show you that we already have the products at hand. Let me come to the properties. That is for our purpose. The point of view that we have at the Fraunhofer Institute of Microstructure of Materials and Systems in Halle, the topic is the mechanical properties. You can see here the benchmark. This is where the high-end toughened polypropylene for automotive application goes. We need a certain melt flow index. We have to have good properties in the injection molding process. That is here the minimum that we have to have. Better would be a higher melt flow index. And we need a certain impact strength. And you can see immediately that we have a beautiful polymer. It's very similar to polypropylene, actually, you can see that the stress, the maximum stress here is approximately 40 megapascals. We have a elongation at break that is going up to 250%, which is really good in the range of polypropylene. But if we want to go to automotive applications, we have to improve the stiffness. Here, the modulus measured in the tensile experiment, which is quite low, lower than we would need. And we have still a problem with the impact strengths, especially the notched impact strengths according to Sharpie. The other values like the strengths and the elongation at break are in the green area, so we can use that material. You can see this tensile bar after tensile testing, beautiful. It really goes quite nicely, very ductile material. Here's the micromechanics. You can see what happens if you have a look on the tensile bar, the cross-section of such a tensile bar in the necking region over here, where the plastic deformation is going to be very intensive. You can see it here. And if you go to detail, you will see that the semi-crystalline structure of the material finally after deformation is completely transferred into a highly oriented fibrillar structure, which is very similar to what we know from polyethylene and polypropylene. So the micromechanics are quite nice, the properties are quite nice. But there's another story. We have the beautiful polymer that we can produce from bioresources. But another story is the processing. We know that processing is energy consumption. We need energy to heat up the polymer. We need energy to run our extrusion processes, the compounding processes, and the injection molding process. And the machinery we need is the so-called direct compounding injection molding, DCIM, which is quite easy from the idea. What you can see here, we have a part of the engine, a part of the machine that is a conventional extruder. You have the extrusion unit over here. You can feed several polymers. You can feed in the PBS base polymer. You can feed it the additives or a master batch, and then you give it directly to the injection molding machine. And then you can produce parts directly in one step without cooling down the material, without doing pellets and then heating it up again for injection molding. So we can couple the extrusion and compounding unit with the injection molding. And that is the way to reduce the CO2 production in the value chain. And moreover, this is ideal for biopolymers, bio-based polymers, biodegradables, because we can avoid thermal degradation because we only have one step of the heating, of the processing. And this makes this machinery perfectly suitable for circular economy and for recycling. So that is the idea with the processing that will be integrated in this mini plant idea that we are going to build. Okay, let's come to the toolbox that we have. So we have been talking about the polybutylene succinate base polymer. Please allow me to show you one more slide that is giving my background, the background of our region. I said that we have the polymer chemistry in our region for, let's say, 100 years. But since 50 years, we are very intensively engaged in the research on polymers. We have a research in the region at the University of Halle, together with a production plants with the industry in Schkopau and Leuna and the University of Merseburg. And what we have done all the years is also the application of electron microscopy to study the morphology of the polymers, to study micromechanical effects. And what you can see here is a stamp coming from the year 1975 with the Academy of Sciences of the German Democratic Republic, had applied electron microscopy, you can see it here, for the research for the chemical industry. So we have a long-standing history, the connection between research and the industry. So what is the idea? We have to find the correlations between the structure of the material, the chemical structure, but also the morphology, the processing conditions, and the properties that we finally need. So we have the polymerization process. The polymerization is based on bio-derived monomers, and that gives us a molecular structure. The molecular structure will be transferred in a supermolecular structure we call the morphology, and that will be influenced by the composition, the compounding, the blend polymers we put in, the fillers, the compatibilizers, the additives, and so on. And of course, the defects that we introduce, like air bubbles and so on. And that gives the morphology. And the morphology is then, let's finally predicting the mechanical properties. The loading conditions come into game and we have the mechanical properties. But now we also have to consider that we have to use bio-based, eco-compatible polymers, but also fillers, additives, like there are pigments to make a beautiful, colorful polymer. This all has to be bio-based. And we have to apply the energy-saving processing, which is the DCIM. And moreover, now the supermolecular structure, the morphology, also can be used to control the degradation kinetics. Yeah, so if we consider that the PBS itself is slowly degrading, but if we can add materials that are faster, like starches, like polylactic acid, then we can control not only the mechanical properties, but to a certain extent also degradation kinetics. So that is what we do. That is the toolbox that we have at hand. We have the PBS as the base material, and now we come on and go with inorganic fillers to increase the stiffness. We can use plant fibers like cellulose fibers to increase stiffness and strength. We can blend it with other bio-based polymers like the polyhydroxyalkanoates, polylactides. We can use starch as granules or as thermoplastic starch. We can use the PBAT as a blend partner, and we can use the bio-based additives like bio-based stabilizers, bio-based pigments. There's also one company, one startup producing such bio-based additives for our polymers. And that is something I will tell you shortly in the end, what we do in our project, that we try to incorporate rubber particles, natural rubber particles, to increase the toughness of the material that we need for the automotive applications. Let me give you a couple of examples. This is just the first example, very classical approach that we just use nanofillers, for instance, a layered silicate material, which is, of course, not a bio-based material, which is a very conventional material, to incorporate the nanofillers here in the PBS to increase the stiffness. A very simple thing, that is the BOC lane, that is the cups that I have over here, these beautiful items that are really of a fantastic grip, of a fantastic properties. And you can see here electron microscopic pictures where you can see how these nanoparticles are incorporated in the spherolytic texture of the polymer. You can see it here in TEM picture. Oh, that is not so amazing. It's just to show that I can do the electron microscopy, because that is what I really love to do. So we have the particles, we can incorporate them, we can finally distribute them. But the problem is, you will see that here in the comparison. That is the pure PBS that you have seen earlier. And this is the PBS with the additive. So what we have achieved now, we have dramatically increased the modulus, the stiffness of the material. Yeah, the stiffness of the material is doubled now. It's beautiful because we have these beautiful porcelain-like, really nice and stiff material, but we are losing the toughness. We are going down. We have now tense elongation at break that is only at 8%, which is not acceptable for the application that we need. Yeah, for automotive applications, we need something that is really tough and of high strength and of high stiffness. So we have to do something. Yeah, you can see it here. We are losing completely the value over here, and we're losing completely the impact strength here, measured as choppy, notched impact strengths. These values are significantly going down. That is something we have to do better. The thing is that also the micromechanical processes change. You can see now here that we have transformed our material to a craze-like process. You can hear the striations over here, which is an indicator that we are now turning into from a ductile to a brittle deformation regime. So that helps us to understand what's going on here at the moment. You can see it here. Yeah, instead of having the nice ductile elongation, you can see that now we have a little bit of fibrillation here, but the fracture surface itself is quite brittle. So we have to do something. Good. The other things that just to show you another example, you can incorporate thermoplastic starches. You have the huge particles over here, which is not quite nice. That is not helping to improve the toughness, but you can see that we have a good coupling between the matrix and the starch particles, which gives us the chance to increase the stiffness, the chance to increase maybe even the strength if we have a good coupling over here, but definitely this is something that helps us to tune the degradation behavior. The material over here is degrading quite fast. We have a deterioration also of the PBS matrix, higher surfaces, and so we can increase the biodegradability by incorporating the starch to the product. Here are another examples. What you can see here is the incorporation of PHB. So this is a 50-50 blend of polybutylene succinate with polyhydroxyalkanoates, the PHB. In that case, you can see the machine directions. We can introduce these beautiful structures here by machining or by processing. You can see over here the PBAT compound. We can control the morphology by the processing parameters. And by the way, this is very similar from the properties and from the morphology, very similar to the polycarbonate blends, ABS polycarbonate blends that are marketed as bi-blend materials for automotive applications. So that is the toolbox we have. And now let me come finally to the project itself. Again, we are just on the very beginning. That is the vision we have. We have done the first experiments that are really promising, but the approach is like that. What do we have to do? If we want to increase the toughness of the material, the ability to absorb mechanical energy, to take up mechanical energy before failure, that is what happens, for instance, if you have a car bumper and you hit the car bumper, it must take up the mechanical energy. So what we have to do in the first degree is we have to control the semi-crystalline morphology. What you can see here, two examples of the spherolytic texture, the semi-crystalline texture, the texture that you can observe in PBS materials. And you can see here the case, if you go to the wrong crystallization temperature or to the wrong crystallization rate, cooling rate, then you get huge spherulites as big as several hundred micrometers, and then you get the defects. You have the defects all along the spherical boundaries here. You can even see that there are voids due to the intensive crystallization, and this material will be extremely brittle. It will be far below the intrinsic mechanical properties due to the defects we introduce. So the aim must be to come here to a beautiful, beautiful fine spherolytic texture that is favorable with respect to the mechanical properties. So we have to control the crystallization kinetics, crystallization temperature, cooling rate, and so on and so on. Of course, we can have a look also on the lamellar arrangement. So the lamellar structures that you can see here in the AFM pictures also play a role. Here, especially, we have to consider the arrangement, if the lamella are parallel, if they are packed in a way like shown over here. And we have to consider the role of the amorphous non-crystalline part between the lamella, because that is what is transmitting the toughness, what is giving the connection between the crystalline area. So one look must also go to the lamellar morphology of our system. That is the business of the Fraunhofer Institute in Halle. And another story is, why not do nucleation? Why can't we introduce nucleating agents to have a fine spherical texture? Of course, we can do that. You can see the picture over here. Here, it does not work. You can see that we have the spherulites that are not at all influenced by the filler we put in. Yeah, so the spherolytic structures are not influenced by the filler, but on the other picture. That is an interesting story indeed. When you introduce, in this case, hemp fibers, this is cellulose hemp fiber material, then you can see that the spherolytic structure or the crystalline structure is growing. The growing of the crystallites starts at the surface of the fiber. So the idea is to use cellulose fibers, nanocellulose, microcellulose, to induce crystallization, to have a fine spherical texture, and on the other hand, to have the strengthening by the incorporation of the fibers itself. So we have a reinforced system with nucleation. That is one of the approaches that we have chosen. So finally, the second approach is to use the classical impact modifiers, the classical toughness enhancement idea. That means if we incorporate small rubber particles, then what we do is when we have a mechanical load applied to the material, we induce deformation processes at these soft rubber particles. The soft rubber particles act as stress concentrators and we produce a lot of mechanical deformation just in the surrounding here in the polar region, in the equatorial regions of the rubber particles. And we do that multiply. So if we have a lot of these small rubber particles, we induce these cracks or micro cracks or crazes in large parts or huge parts of the volume. Very nice. Yeah. And then the rubber particles can act, for instance, as crack bridging agents. They can stabilize the cracks, and they can act also as crack stoppers. So you can see that here, lower magnification. This is a polystyrene. This is not the PBS. This is our example, our model system. We have the polystyrene. And if you add the rubber particles to the polystyrene, you can see that there are many of these deformation zones. The crazes are produced. So the energy dissipation is multiplied in a huge volume of the material, giving more toughness to the material. And you can see even here that the crack that is running in here is stopped by such a rubber particle. So that is the idea. The classical mechanism that was found in the 60s of the last century, we are going to apply this to our polybutylene succinate. Yeah, that is the idea, to do the toughness enhancement by incorporating of the rubbers. The aim is shown here. What we want to do, that is the target of our material. We want to go into applications in automotive industry. We want to go to bumpers. We want to go to parts that you can see here. We want to go to interior parts. And that is the benchmark we have. That is polypropylene, EPR or EPDM mixture for toughness enhancement with the nanofillers that we have seen also earlier for our PBS. And this is the classical ABS system, also with this rubber modifier particles. That is the standard. This rubber toughening, this is the standard in automotive industry, and we just want to apply that to our material. That is the status we have. We have now identified a set of natural rubber particles that are cross-linked. You can see it here. This is the natural rubber in different sizes, different qualities. The quality of natural rubber depends on where you get it from, which plants are producing, which areas producing the rubber. And we have just figured out now what is the ideal size, what is the ideal way to cross-link the rubber particles to get them into the material. And the other idea is, of course, we have a lot of rubber coming from tire recycling. Yeah, we have rubber powders that are ready to be incorporated in our PBS. The problem is that these rubber particles are still too big. They are not working as toughness modifiers. Yeah, the particle size with 400 micrometers is just too big to introduce these favorable mechanisms. So we have to go the way here with the natural rubber spheres, the natural rubber cross-linked particles. That is what we have found. Yeah, we have particles now produced in the range of 100 nanometers to 1 micrometer. What we expect is the optimum particle size for the toughening. And we have even found that there are some systems that are grafted with methyl methacrylate that have a bimodal particle size distribution that we can also try to get the optimum particle size, particle distribution, and interparticle distance. But that is exactly the status where we are at the moment. What we have to do the next couple of months to get the product ready. So let me come to a short summary and outlook. We are sure that PBS is a good candidate for bio-based material polymer, a bio-based polymer toolkit for even demanding applications, for interior, exterior parts, for automotive applications. I see that there is a high potential to replace the polypropylene, to replace heterophasic polypropylene, LDPE, HDPE grades. That is on the horizon already. To answer the question, maybe we can adjust the polymers to be stable during their service time. I agree that it makes no sense to have a car bumper that is biodegrading. Yeah, but the material can be adjusted to a system that is stable during service time, that is recyclable. And if there is no other way, it can be biodegraded under defined composting conditions. The stability, degradability, mechanical properties like stiffness, strength can be tailored by blending with other bio-based polymers, biodegradable polymers. The problem is that at high melt flow rates, which is low molecular weight, finally, that's the same. We have low molecular weight. Then there the PBS suffers embrittlement. We have a ductile to brittle transition, and this goes along with the yielding to craze-like deformation mechanisms. That is, even with the inorganic filler addition, it's even getting worse, as expected. So our strategy is to do toughness enhancement, good balance between MFR, appropriate molecular weight. That means entanglements must be there in the intercrystalline amorphous phase, time molecules, entanglements. We must control the crystallization, and we have to apply the classical strategies for toughness enhancement. That is the project we have. Good. Coming to the end, I have shown you in the beginning the ugly side of chemistry that I was facing, or that I grew up in the chemical region. Yeah, I grew up in an area where we had all these chemical industries around, and that was really something very dirty, very ugly. We had a lot of nature that was devastated by the carbon mining, for the coal mining. And that is the situation we have now. That is a picture really recently, just done a couple of days before. Now you can see that was a coal mining area. That was such an open cast brown coal mining region. And after 20 years now, it has transformed into a beautiful recreation area. This is one of the biggest artificial lakes on the world. Yeah, we have now campsites here. We have nice beaches here. You can do water sports. That is something, that is what I see, what could be the transformation from fossil to bio-based materials. Thank you very much.
Thank you, Sven, for the really overview of this connection between the bio-based polymers to the mechanical properties, and can be also these materials can be changes for the not the classical fossil polymers.
Yeah,
so
yeah.
we have time for questions.
Yes, please.
Alguien que tenga un micrófono.
Hello, good morning.
Good morning.
I have been working with bioplastics more than 10 years, and what I have, I work in the production of the bioplastics, basically with PHB and
Yes.
the fermentation processes, right? For lactic acid and so on. So what I have observed is that in order to extend the use of these polymers in the industry, there is an issue, which is the availability of the polymers. I mean, for example, in Mexico, we don't have an industry dedicated to the production of PHB or any other of these polymers. So industries interested in the processing of these polymers, they have to import them. So the costs, of course, increases. So do you have an opinion about the availability of the worldwide availability of these polymers, and all this related with the costs about PBS, for example? Is it very available for its use? Which is the situation?
That is indeed the most important question. There is a joke that I do when I go to my lectures for polymer science. I say the most important physical property of a polymer is the price, which is a stupid saying, but that is exactly what we are facing. The material is still very expensive. We have limited resources to buy it. At the moment, we buy the PBS in China. The production facilities are very low. But what I see at the moment, that is what I've learned from the conference I just attended, that right now there are many, many small companies, small and medium companies, even larger companies, starting to increase the production of polyhydroxyalkanoids. Yeah, small enterprises that are looking for new ways to produce PHB, PBS, polylactic acid. And I think that at the moment that there is regulatory work done, when the price is not that important anymore because there are other factors, then we will have an increase in the production. I'm absolutely sure that the production facilities will go up. I have just learned that one of the companies I have in my surrounding area just went broke. They have produced bio-based polymers. They went broke because the price is too high. But that is something I believe that will change now, that we have an increase in the production facilities for PHB, production facilities of PBS, and all the other interesting biopolymers. What we have to deliver is we have to show that we meet the properties, that the materials are really have the potential to replace the plastics that are cheap. Yeah, and we need the regulation. In that case, I'm positive that we will have success. You are right, that's the problem.
¿Alguna otra pregunta? Si requieren asistencia para traducción. ¿No?
Hello. Hi.
Hello.
Thank you so much for your talk. It was really interesting to see how all the stakeholders get together to go from biomass to a product that can be applied. So that's really interesting. I'm not from Mexico, I'm from Costa Rica. In Costa Rica, we have a lot of biomass as the same here. So I was thinking about the characteristics of this biomass that you use to get the monomers, to get the PBS. So there are some important characteristics to get these monomers. Thank you so much. And great microscopies. I like it a lot.
Yeah, that is also a very, very good question, very interesting point. I have to say that I'm not a chemist and not very much involved in biochemistry. I think that there are many, many ways today to get the feedstock. What you need is sugars. Finally, you have to convert your things to sugars, and with the sugars, that's the same with the PHA. Then you are ready to do all the cycles, to do all the chemistry. What we do is we have lignin in mind, we have starch in mind, we have cellulose in mind, we have all that you can transfer to sugars. But I'm not a specialist in biotechnology, unfortunately. But what I can see is that at the moment, that is what I've just learned, is that the biotechnology is, in this sense, on a revolution. There is a state where now obviously, the processes can be controlled to get from different feedstock sources to sugars, to the materials that you need for the fermentation, that you need for the production of the monomers. Again, I'm not a specialist, but there's one thing that is most important to me. If we talk about the production of plastics, commodity plastics or high-end plastics, whatever, we must take care that we do not produce another problem, that we do not go into deforestation of the rainforest to produce sugarcane to get polymers. I think that's the wrong way. And the approach we have is to go with waste, with food waste, to use food waste, to use green cut from the gardens, to use grass. My colleagues in New Zealand, they use seagrass. They use seagrass to produce PHB. So that must be the approach, in my opinion.
Muy bien, muchas gracias. ¿Alguna otra pregunta?
Hello. Yeah.
Hello.
Hi. My name is Guillermo. I'm working here in the Department of Wood Cellulose and Paper. I have been working with nanocellulose for many years. And yeah, I guess you have tried, right, nanocellulose with the PBS. Is that correct or not?
Yes. Yeah.
Okay. So what would you say is the main advantage of using nanocellulose in this polymer? I mean, it increases elongation of break, or
yes.
What is the advantage?
It increases mainly the strength and the stiffness. But the main importance is that we have the effect of the nucleation. We can achieve a complete transformation, because the problem is with the PBS, it crystallizes very, very similar to the PHB. Yeah, it crystallizes nicely. It has a high degree of crystallinity, and the tendency is to form huge cerulites if you don't do something against it. And one idea is to use the nanocellulose, to use the mechanical properties of the cellulose, And on the other hand, they use the nucleation effect. So that gives a very fine structure. And due to this effect of the nucleation, of the epitaxy of the polymer on the surface of the cellulose, we have a very good interaction. We have a very good interlocking between the fibers and the polymer. And that is something that gives us much better properties than just to give wood floor into PBS. Yeah, so we have a very nice balance, toughness, strength, and modulus. That is the aim. Hello? Ah, now I can see you.
Yeah.
Sorry.
Yes, again, sorry. It was inconvenient.
Yeah, that was understood. I think
Yeah.
you repeat it again. But just another question, just a last one, really quick one. You said that the rubber particles from the tire are not working because of the size. That's correct?
Yeah.
Okay, so what size would you say is the...
That is a very good question. That is exactly one of the aims of the project, to figure out what is the optimum size. But we expect particle sizes in the range between some 100 nanometers to 1 or maximum 2 microns to work, because the problem is not only the size of the particles, the problem is the interparticle distance. We have to arrange the ideal interparticle distance so that we have an overlap of the stress concentration to evoke micromechanical processes in the material. Yeah, that is the idea. So we need the ideal interparticle distances. And if you have huge particles, if you have this 500 micrometer rubber particles, then the whole process will die down. It will die out. It will not work properly. Yeah, that's the problem. We have to go to small particles.
Okay, thank you very much.
Thank you very much for this very, very interesting talk, Professor. So we are working in similar topics with bio-based polymers. So one of these topics is the recycling of these polymers. Especially we are working right now with PLA or PBS, or PHB.
Yes.
Actually, we want to work with PBS, but it's a material that is very difficult to get in Mexico. So we are trying to get the material. So what are the challenges that you have identified for the recycling of these PBS?
Yes. The main problem is that all the materials are quite sensitive, like many of the polymers, but especially these polyesters are quite sensitive to thermo-oxidative degradation if you go into processing. So that is something we have to keep in mind. So we have to get the temperature to a reasonable level. And that's why we have introduced a special processing unit that at least saves us the second heating cycle. Yeah, that is one thing. That is something that is also important for recycling. Yeah, if we have a material that is already damaged by thermo-oxidative processes, it gets harder and harder to get it into the second or into the third cycle. The second point is, of course, we have to organize the collection. We have to organize that we have a clean collection of the PBS, because PBS must go with PBS to go to recycling. But that is a system that is quite well developed in Germany. If something works in Germany with the recycling, then it's the collection, the clean and special collection of the different polymers. That is quite good organized. Yeah, and that is the point we have to see. And I forgot the last thing that I wanted to say. I'm sorry, but that's it. We have to collect the material. We have to we need the additives. We have a company here that is producing stabilizers, thermal stabilizers based on wood products. They are going to, for instance, to walnut. What is that? Some nuts. They get to the shells of some nuts and produce scavengers. They produce antioxidants from natural products, and that is another thing. If you make the decision that you want to go with your bio-based materials into recycling, you have to treat them very much the same as you would do with the commodity plastics. Yeah, you have to take care to avoid thermal degradation. And that is something we have to get the balance. We have to decide, do we want to have something that's biodegradable, or do we want to have something that we can recycle? That is still the balance, to find the balance between these items. That is science, that is research we have to do.
Okay, I think it's time for finish the question session. And I would like to thank Dr. Sven Henning first of all, to accept to be part of this inaugural conference. And he's really enthusiastic. You want to connect to him, and he's open to collaborations. Please be able to do it, because every time he's trying to help people and to be connected in this field of the biomaterials. This is the really good opportunity for us. Thank you, Sven.
Thank you very much.
We see you in a round.
Thank you.
Bueno, muy bien. La siguiente parte